Right. Okay, let me get my slides up here. So when I'm sharing my screen here, are you all seeing the participant list and the other stuff at the top, or just my slideshow?
Just your slideshow.
Just your
Okay.
slideshow.
Okay, let me get rid of this then. Okay, so I'm just going to give a brief introduction to what js9 is. I probably have more slides in this slideshow than I'm going to need. We can skip over the ones that we are not going to use. I would like to make this a working session. I know one of the biggest things with being a teacher or professor is being given a new tool, but then never having a chance to practice with it. So I'd like this to be more of a working session where you can actually do the activities yourself when I'm here to answer questions for you. I did paste the link to the slideshow in the chat, and there's also a QR code on the screen. My email address there, if you want to jot that down after the workshop at any time. If you have any questions on any of the activities, you're more than welcome to email me and I will help you with that. All right. So js9 is a web-based application, and it displays the information that's in FITS files, and it also has a lot of analysis tools that we'll be looking at today. It runs on pretty much anything, even phones, which my students have tried to do sometimes. To me, it's way too small to use on a phone, but I think just the excuse to be able to pick their phone up is why they do it that way. It used to be DS9, and this was software that you had to download to your computer, which meant that unless you were really friendly with your IT department, sometimes it was hard to use, but now it's web-based. All of the activities are written so that you never have to have used a js9 before to do one of these. All the commands are in pull-down menus. It's really easy to see. I'll have you go through some so that you can see how the instructions are written yourself later on, just to see how easy it is to use. So we have several activities that are pre-written. These are kind of meant, they can either be used as a standalone activity to teach a specific thing, or doing the whole series of activities. Each one of these teaches a different js9 analysis tool, so that by the time students have gone through all of these activities and they see what kinds of things js9 can do, then they can do their own research projects with on their own astronomical objects and import their own FITS files. So this is a rundown of the pre-written ones. We're going to go through several of these today. The first one is making 3-color composites. The other one is looking at energy spectra to classify supernova remnants as type 1A or type 2. Light curves to differentiate between white dwarfs and neutron stars. Looking at star formation in the Cartwheel galaxy and determine what the sources of the ultra and hyperluminous X-rays are. So in that activity, we're looking at information in the X-ray band and also in the visible band. Also looking at the expansion rate of supernova, and then there's a new one looking at the bullet cluster in various bands of the electromagnetic spectrum for evidence of dark matter. So this is the website that you should have up now. This is where the js9 software resides and also where the activities reside. So if you could pull that up now. So this is just the regular Chandra website with the js9 extension added to it. There are also lots of other educational materials there, as well as a photo album where you can find observation ID numbers so that you can pull all sorts of objects into js9. The first one that we're going to do is 3-color composites. I do have slides. This one's fairly easy. If you would like to click on, you should see over to the right-hand side, you should see a list of the activities. So if you want to pull the PDF file up to look at the instructions and do it that way, those are written with students in mind. With the exception of the bullet cluster one, they've all been used in many, many classrooms and tested over and over again with teachers and students, and they're pretty student friendly. But if you want to see what the students would see, if you click three color composites, it's the one we're going to do to start with. So I was saying earlier that probably some of my slides I really don't need on here. I left them up. I'm sure you all know what representative color images are. One thing that I do like about JS9 is under the view menu, you can pull a pixel table up that is photon intensity and kind of run your cursor over the object so that students can see that there's actually numbers behind each one of those pixels, which is a cool thing. Also, please feel free when I'm talking, if you have questions on anything, just go ahead and interrupt me. That's fine with me.
I'm a little confused. What should we be looking at right now?
Okay, so if you go to this web address here, the chandra.si.edu/js9,
Mm-hmm.
I'm actually going to bring that website up myself in a second. I'm going to get out of my PowerPoint
Okay.
so that we can do an
Okay.
activity together.
Okay.
And then we're going to do the three color composites activity to start with. So I will get out of this PowerPoint slide and I'll show you where that is.
Okay. All right.
So I have all this on slides. Sometimes when I present, I only have an hour. I'm just going through things quickly, and I have the instructions up on the PowerPoint slide itself. I don't know what's easier. It's hard for me to both demonstrate it on the program itself and have my PowerPoint slide up. So if it's easier, it might be easier for me to just, if you guys have the instructions open and I can show you where they are, it might be easier for me to just show you right on the software itself than to just give you a PowerPoint slide with instructions. So do you all have this web page up here that says Science Olympiad at the top?
Yes.
Okay. And then three color composites, if you click here where my little cursor is, those are the instructions for the activity. So you can make three color composites different ways in JS9. One way would be, this is X-ray data. So this is the Cassia supernova remnant, which I'm sure you've seen many times. One way to make a three color composite with JS9 is to use the X-ray data and just color low energy X-rays red, medium energy X-rays green, and high energy X-rays blue. You can also make three color composites based on different bands of the electromagnetic spectrum. So if you wanted to use infrared data, visible data, and X-ray data, you could also make a three color composite that way. But we're going to do one with X-ray data to start with. I just find this useful. It's fairly simple, and I find it useful as a first activity, just so students can understand that these colors do represent certain things. So if you go under analysis, and then you go to event filter, over here, it shows you the format that you need to type it in. So you need to do energy equals. And then for the low energy band, we're gonna ask it to just show us the photons that are in the energy range 600 to 1650 electron volts. So 600 to 1650. And then you just hit run. Is everybody with me so far? Please tell me if I go too fast. Okay, now you can also change the scale here from linear to log if you want it to be a little bit brighter. So that was scale, and I changed it to a logarithmic scale. And we're going to color this one red. These are the low energy X-rays. When you go to do the next band of X-rays, under File, you should now see your original file that had all the photons in it. And then you should see the file that I'm looking at right now that just shows the photons from 600 to 1650. When we do the next energy cut, we want to make sure that we go back to our original file, because if we are now going to ask it to show us photons from 1650 to 2250, if we use this one, we're not going to get anything. So we want to go make sure you go back to your original file. It's one of the things, I mean, I teach high school, but one of the things my students would always do is they would do the next energy cut and it would come out black. So make sure you go back to your original file. And then just go to event filter again. And this time we're going to do 1650 to 2250, I think is what I said. Yeah. Run.
Pamela, I'm just going to interrupt you here. We
Sure.
have a question in the chat about seeing your screen, and I wanted to clarify that with Diana. Because
Okay.
I can see it now. Sorry,
Oh,
I was
okay.
somewhere else. I can see the screen. It's a bit fast for me, by the way. I
Okay,
cannot
please.
manage to follow and do everything, but I can see it.
Okay, yeah, please tell me to slow down if I'm going too fast. I didn't hear anybody saying anything, so. Are you also finding where the instructions, the written instructions are?
Yes, I found the written instructions, but I
Okay.
don't have the time to just read and input the numbers and see what you see. But yeah, I have everything.
Okay. So I can, I'm gonna do the last energy filter in a second, so I can make sure that I go through the process again one more time on the last one. So basically, I'm doing the same thing 3 times. I'm just gonna change the scale on this one to log, and I'm gonna make this one green because this was my medium energy X-rays. So this is the process one more time. It's the same thing that I've done the first 2 times, except for I'm just going to input different numbers for energy range. So
Can you
go to,
just pause for 2-3 minutes? Let us like arrange our screens and all of that.
sure.
The files.
Let me know when you're ready and I'll go on.
We are behind, sorry, unless
That's-
somebody else.
That's absolutely fine. I can't see your faces, so I don't know who's with me and who's not. Yeah, totally fine. Just let me know when you're ready. I can also start over if you would like me to. It doesn't take a super long time, so let me know also if you'd like me to do that.
I'm all for starting all over again. Yeah, it will
Okay,
be
sure,
great
no
for me. I
problem.
don't know everybody else, but.
No, that's fine. So let me know when you all have a screen that looks like this. This should be the default screen when you log into that website.
So Leela says, yes, she's there.
Okay.
Mine is red. I click the refresh button, but I don't know
It's
how to
okay.
start.
It's okay if it's a different color.
Okay.
I know that it randomly picks a color. If you notice under color, there are all sorts of different color schemes. And I know that often it picks a random one when you first log in. So as long as you have Case on your screen, which should be the default FITS file, it could be colored different ways.
Are you sharing your screen right now?
Yes.
Other window. You have to find. Sorry.
I imagine it's a bit tough because if you've pulled up this on your site or on your computer and you're trying to look at Pamela's screen, they're going to look identical right now. So it might be a little tough to tell.
What should be the scale to have the same picture?
So this, I haven't done anything yet except for just, this is just the default web page. And when you're ready, I can explain what you do next, but I haven't done anything yet. Is everybody ready for me to move to the first step?
I'm ready. I don't know. Yeah, I'm ready.
So what we're trying to do is this shows all the photons in the observation by the Chandra X-ray Observatory for this particular observation. And what we are doing is we're going to go to Analysis and Event Filter. And we're going to use the event filter to ask it to only show us the photons within a certain energy range. So click Event Filter. And there's an example over to the side. It says energy equals. And we're going to go from 600 and then a colon to 1650. So this is the energy in electron volts. We want it to only show us the pixels that have photons with these energy ranges in them. And when you've got that typed in, then you just hit run. Is everybody okay there?
Mine is black and white when I hit run.
That's fine. Okay. That's because the color that it's picking is grayscale. So we want to make this red because we are going to make a red, green, blue, 3-color composite. So since these are our lower energy X-rays, we're going to color these red. So I'm going to, under color, I'm going to go to red. And then also just to make it a little bit brighter, under scale, I'm going to change it to a logarithmic scale instead of a linear scale.
Finally, I have the same view as you. It's just my scale said up to 21, and I saw yours as to 35, and I don't know how this matters. I've changed that. Yeah.
If as long as this looks like my screen, I'm not exactly sure what you mean by 35. Are you looking at the green numbers at the top or?
When you click on scale, there is low and high at the very bottom. See, is
Oh,
there
don't worry
low,
about that.
zero? Yeah.
No, don't worry
okay.
about that. That's fine. Don't worry about that at all. Okay?
Mhm.
Okay. Now we want for our medium band, which we're going to color green, we need to go back to File and we need to choose our original file again. So go to File, choose the original file again, which is Case Fits. and we're going to repeat the exact same thing that we just did, but with a different range of energies. So we're going to go to analysis and event filter. See, I'm lucky. I printed the instructions out on a piece of paper, so I didn't have to keep switching screens before I came. If I had thought, I would have mentioned that that might be good. Okay, so go to event filter. And we're going to do energy equals then again. And this time we're going to go from 1650 to 2250. And then run. This time we're going to make this one green because it is our medium range of.
Sorry, can you repeat on the file part? Which one did you open? When you clicked on file before analysis?
You want to go back to your original file, Casse Fits,
Yeah, okay. Thank you.
because if you use the one that you just had colored red and you asked it to see the energy from 1650 to 2250, you would get a black screen because that range wouldn't fall into that other file. So this original, you need to go back to your original one each time you do this.
Mine says error, can't find open input file.
So when you did that, when you did your energy cut, did you go back to your original file? Did it look like this?
Yeah, I'll go back again to make sure. Thank you.
Also, you need to make sure that it's exactly in this format here, energy equals, and then the two numbers separated by a colon, but no quotes around them. So you want it to look like,
Okay, like the example. Okay.
okay. Okay, so I'm going back to that one. We want to make this one green. And again, I'm going to change it to a log scale just so it's brighter. And then we're going to do one last energy cut for the higher energy X-rays. So we go back to your original file. Event filter again. So there are all sorts of different tables and arrays within a FITS file. Some FITS files have different things. Event filters can sort under all different things. This particular FITS file does have tables for energy. That's why we're able to do this. So there is a table with a header that says energy. And then for the last one, we're going to go from 2250 to, forget what I said, 7500. And I got those numbers by looking at another 3-color composite, but I also know that the range that most X-rays FITS files have in them too, so I kind of just broke it into 3 parts. So the numbers are a little arbitrary, but I was just trying to divide the whole thing into about 3 parts. And then the last one, you are going to make blue. And again, I'm going to change the scale to log. Okay, and then here's the fun part. Once you've done that, you're going to go back to color again, and you're going to hit RGB mode. I'm going to let you guys do it before I do, so that you can see what it looks like without me spoiling it.
Pamela, I have a question.
Sure.
Is it possible to delete one of the files that you have if you've made a mistake?
Absolutely.
How do you do that?
You can just go to File and click which, like say I wanted to delete the one that I have on.
Mm-hmm.
So do you see do you see the check mark next to the one that I have open?
Yes.
And then do you see where it says close?
Yes.
You can
Thank
close
you.
this image.
Perfect. Thank you.
Mhm. And then hopefully you have something that looks kind of like this when you go to RGB mode.
Joe, can you elaborate? Why did you get a blank image?
Who got a blank image?
In specifying my photon energy range, I used a dash instead of a colon, and it parsed that, but it gave me a blank image, and I
Okay.
had to delete that image, just like the lady just asked. I had to figure out how to get rid of that image, and then I went back and did it again, and now I have a beautiful composite. So it worked.
I'm at the like all of the colors, and when I go to file, I don't seem to have the option to delete one of the colors. So mine doesn't look like this.
Okay, so when I hit file, this is what mine looks like. I have the one that I colored red, the one that I colored green, and the one that I colored blue. Do you have something that looks like that?
I don't have the upper section. Mine starts from files and display, and I don't have the upper section that you see. But maybe
When you
it's in the
hit file,
process.
you don't have this list here?
No, no, I don't have the list.
On
you-
mine, I had to slide over to images once, and now it's displaying the correct way. I'm not sure what happened there, but I got the same thing she got at first.
Mm-hmm.
So when you try color RGB mode down at the bottom, does it work?
Yeah, that works.
Then that's
I can,
fine. That's
yeah, I
all
can
you
see,
need.
yeah.
That's
Okay.
all you need then.
Okay.
Okay. There
It's-
are all sorts of different filters and stuff that students could play with if they wanted to. You can see that this one's kind of pixelated and grainy. So I'll go back to my slide in a minute, but there are all sorts of image filters that you can play with if you want to. So where I found that was under view and image filters. One of my students, after we did this activity, and I told them to play around with the filters. And I was, this one doesn't, if you play with the blur a little bit, this kind of looks more like the ones that you see, as a public release image where it's not quite so pixelated. So you can play with all sorts of things. I was told that the astrophysicists that put together the public release images that look so glamorous that they actually fight over the ones that are really good at their jobs. And one of my students said, wait a minute, you mean I can be an astrophysicist artist? I want that job. When she realized, what artistic choices you could make in putting together, a public release image, she thought it was really cool. So that's not necessary, but it's something that you could play with if you wanted to. Does anybody have any further questions on this particular activity? Okay.
I found a very interesting effect quite by accident. That would be really interesting to show students. My 3-color image did not look anything like yours. And I'm like, what the heck? So I went back and looked, and one of the files I had accidentally put, instead of 600, I put 500.
And it changed it that
And
quick?
it actually changed, it made it more blue. It was very interesting.
Oh, the other thing too is, and as far as other things that you can do, if you go back like just to your red image, if you hold your mouse button down and swipe sideways or up and down, you're changing the contrast and bias. So right now I had my red image selected, and you can see that as I'm going back and forth here, I'm changing the amount of red.
Uh-huh.
So you can go down and adjust the amount that each color is in the image too, and play around with a lot of different things.
Yeah.
Just again, so that students understand that it's the same numbers behind each one of these pixels, but the image can look very different depending on what the scientist is trying to show.
This is also great when talking about color, in that color is an illusion. It's whatever the image processor decides that they want it to be. And that ultimately you just got photons and energies.
Right, and so if you go under view and you go under pixel table 2 and hover over the images here, probably I should go back to my original, but you can see, like, if I'm pointing at the neutron star in the middle, I mean, you can see the numbers on the pixel table too. You can also, one thing I find helpful too is, like really zooming into the picture and showing students that it really is made up of a bunch of little squares. We also have with my high school students, I thought it was too simple. I thought it was a middle school activity, but it turns out it wasn't at all. We actually have a paper and pencil one that is, there's a bunch of numbers here. Students find averages and they fill in the missing pixels, and then they color the image themselves, and they decide how they're going to bin the colors and what colors each range is going to be. And this is actually based on the Casey Super. I mean, I think this one is what, 11 by 11. So there's 121 pixels, whereas the one that you're looking at, has millions of pixels. But when students color it, it's crazy how different one students can look from another's just by their color choices and the way that they bin the numbers. So I usually actually start with the paper and pencil one and then have them go to the js9 one. It seems like whenever I skip this one, the whole idea of representative colors is a hard thing for them to understand.
I have a question.
Sure.
Have you ever had students who were colorblind? And if so, how did they fare with this activity?
I never have had students that are colorblind, but my husband is colorblind. I should ask him. He has no cones in the retinas of his eyes. So he's completely colorblind. Maybe I guess you wouldn't make a 3-color composite because it wouldn't make a lot of sense, but you could also even just have, if you play with grayscales and even just try, looking at the difference between a linear scale a log scale, you know, what kind of features you can see on the supernova remnant. You know, with the linear scale, I didn't really see that big blowout on the side. You know, I'm just seeing this general part here. You know, where do I see the inner shock wave? Where do I see the outer shock wave? You know, what does the square root filter show me? Here's the inner shock wave. Here's the outer shock wave. You know, here's this little blast pouring out. Maybe looking at it that way instead. But to also show them, even just with the different scales, even without different colors, that there are still choices on how the images are shaded depending on what it is you want to see. You could also have them, you know, change contrast and bias too. And the underlying pixel table, the numbers still haven't changed, even though the image itself is changing. Did that answer your question?
Sure.
Okay.
I'm also curious at the js9 site if you give the students the whole range of photon energies and then have them decide individually how they want to bin red, green, and blue.
Oh, they could. Yes, you could.
And then they would see how very different their different images were depending on how they chose.
Yeah, absolutely. And as a matter of fact, if you just wanted to know what the total energy was, we're going to use this in the next activity. But if you do an energy spectrum, it at least gives you like a range here so you can see what the energies are total in electron volts. And then they could decide here how they wanted to bin it. So from about 0 to 8,000 or so.
Very cool.
I'm going to show you this later too, but I actually usually change the y-axis on the energy spectrum. I usually change it to log because I think it's kind of easier for me to see. But I'll explain that later. Any more questions on this one? Okay. So, you know, definitely I'm not going to get through every single one of these activities, but I think it's almost more important to let you play with a few to get familiar with it yourself instead of me just saying, these are what you can do in all these activities and just mention it, but you never get to try it and ask questions. But if anybody feels like they need anything else or want me to change the way I'm doing it, I'm flexible. Okay, so this is what we were just talking about with playing with image filters. So I just showed you an energy spectrum, and one activity that students can do is determine if it's a type 1A supernova or a type 2 supernova by the energy spectra. So by looking at the elements. I really like this periodic table, so I show this one to my students and some cute quotes. I'm sure you've heard the Carl Sagan one. I also like We Are Stardust from the Joni Mitchell song. So just showing where some of the elements come from. There's also a cool YouTube video. I wish I had put the link on here. I forgot to. That kind of talks about the origin of the elements as, you know, in the universe and where they come from, the ones on the periodic table. Do I need to go over type 1 and type 2 supernova? I don't want anybody to feel bad of saying yes, but I wasn't sure. I'm not sure like what everybody's background is and if I needed to talk about that or not.
How about just very quickly?
Sure.
Recap.
Okay. So in a type 1A supernova is when you have a smaller star like our sun that eventually becomes a white dwarf. If it's in a star system, in a binary star system with something else that eventually becomes a red giant, the white dwarf can suck material off the companion star. And when it reaches the Chandrasekhar limit of 1.4 solar masses, then it triggers explosive nuclear fusion. I think it's wild that it explodes in about 10 seconds. One of the big things about the type 1A is it does not leave any remnant in the core of the supernova remnant. There's no core remnant in the supernova remnant. A type 2 supernova is from a more massive star, where when the nuclear power source is exhausted and the core collapses due to gravity in less than a second, depending on the mass, either a neutron star or a black hole can be formed. So we were just looking at the Cas-A supernova remnant, and you may or may not remember, but I had pointed at a tiny little white dot in the center of that is probably the neutron star. So on a type 2 supernova, there is a core remnant left. So in this activity, and I will again try to go slowly. One thing, if you do pull this one up, so let me go back to, I'm just gonna hit. If you do pull this one up, when we're identifying elements, there's a table that we need. So it's a little hard. I should have split screen, but then everything is too small. We're doing the X-ray spectroscopy of supernova remnants right now. We're trying to decide if the supernova remnant is a type 1A or a type 2. So we're going to be looking at 2 representative supernova remnants to start with. We're going to be looking at Tycho's supernova remnant, which we tell the students is a type 1A. And then we're going to be looking at another supernova remnant that doesn't have as easy a name to say, and I always forget what it's called because it's just a bunch of numbers and letters. But we're going to look at a representative type 2 supernova and compare the 2 spectra and the elements that are in them to see the similarities and differences and how you might be able to tell the difference between the 2. And then once the students have looked at a type 1A and a type 2, then they can look at other supernova remnants and classify them as type 1A or type 2, depending on what elements are in their spectra. Does that make sense so far?
Mhm.
Okay. So I will show you how to get these observation ID numbers at some point. The website that you guys are on right now, if you take off the js9 extension, it's just the regular Chandra website, and they have something called a photo album. They have the photos grouped by type, like supernova or galaxies or whatever. And when you click on one of those photos, down at the bottom, they have a facts section, and there's a number called an observation ID number. So this unofficial Chandra archive search page, I just happen to know you can do object name, or you can do Chandra observation ID number. And I just happen to know the one for Tycho's supernova is 115. Okay, so I went to analysis. Actually, let's close this guy out. There's a lot of data in there that we don't need. So let's go to close this image. And then we're going to go to the unofficial Chandra archive search page. And I'm going to type in the number 115. So this is a really early Chandra observation because they're up in the, I don't even know now, 20,000s now. And this is observation ID 115. You hit search. And then to get this into JS9, this is how easy it is. Under where it says title, just drag this link over into the JS9 window and drop it.
Oh.
You see how good the public library's Wi-Fi is? Okay.
I'm sorry, what do you drag over?
Okay, I'll show you. So in the Chandra search,
Right.
once you hit search, there should be a link over here under title.
Okay.
Just drag that link over to this window. They didn't used to put a spinning wheel while it was thinking when it was DS9, and the students always just gave up. They didn't realize how much data was getting loaded in there. One of the other things that students find really cool is that you're actually like talking to computers. I think this one is at Rutgers University. So it's kind of cool that you're actually telling a computer at Rutgers University what to do and what analysis you want it to do for you. So this is all being done somewhere else, and it's not being done, you know, on the student's computer. You're talking to another computer, another server. Is there anybody that doesn't have this image up? Okay.
Yes, there's Leela isn't there yet.
Okay, I'll wait. Thank you for somebody else monitoring the chat for me.
You're welcome.
I'm
It's
trying to
hard.
put things and my screen's not that big, so when I
Exactly.
put the chat up, it covers half of my screen and I can't see what I'm doing.
Yes, it's hard when you're a presenter. So having a Zoom monitor is really nice to have. So is everyone here yet? Oh, Leela asks, where do you type 115?
Okay, click the unofficial Chandra archive search page. So this button here. And then 115 where it says Chandra OBS ID, that's the observation ID number. That's where you type the 115. And then you just click search. And then the link that's under title is what you drag over to the js9 window.
Great. Is there anyone else who's not at this point yet, or can we move on?
Okay, so the next step in here does say to put a circular region around, and I think it works without this. But just to point out regions, if you want it to make if there were a particular area of the supernova rim that you were interested in, like maybe we want to know what's the spectrum of this really bright spot right here that I have the green circle over, I'll delete that region out. So I just went to regions and I went to circle. If I want to look at the whole thing, I might drag my region around all of this so that when I do my energy spectrum, it includes the whole thing. So I think if you do not put a region on, it just by default will do the whole thing. I just wanted to point the regions out because there may be a time when you're wondering if the elements in one section are different than the elements in another section. So I don't think you have to do that. But the energy spectrum is under analysis again. So under analysis is where you're going to find obviously all the analysis tools. So if you wanted to make light curves, we used the event filter. If you want to do an energy spectrum, there's all sorts of different kinds of analysis tools. These analysis tools are not necessarily going to work with every single FITS file because every single FITS file might not have the information to do all of these things, but they will definitely all work with any of the Chandra FITS files. So you're going to click energy spectrum.
And I did not set an aperture and I got the same spectrum that you got. So you were
Right. I think by default, it does the whole thing. So the only reason I put the regions on there was just in case you might want to use them later if you only wanted to look at a spectrum of a certain piece, just to point it out to you. Like Cassie that we were looking at before, in the upper left corner had like some kind of a weird jet coming out of the side. So maybe if we wanted to know what elements were in that particular jet, we could just put a region around that jet and just do an energy spectrum of that piece instead of the whole thing. Okay, so each one of these peaks represents an element in the spectrum. I personally think it's easier to see this if you go to the cog in the corner and change the y-axis to log instead of, you don't have to do this. If you change the y-axis to log, I find even this little tiny bump here, each of these small ones represents an element. I'll go back to the table in a second. To get a few more significant digits, if you draw a box around a peak, and then look at where the peak is, this is in electron volts. So to get a few more significant digits, if you can zoom in on each of the peaks to get a better number. And then these blue arrows up in the corner will take you back to your original graph. So you would want students to look at each one of these and determine which element they correspond to. So we have emission lines here sitting on top of this like general shape here. This general shape underneath is bremsstrahlung radiation. Supernova are really high energy plasmas, and bremsstrahlung radiation is, I think bremsstrahlung is German for breaking. Somebody else that's an astrophysicist can correct me if you want to. But so there are a lot of positive nuclei and then kind of loose electrons. And when an electron gets close to a positive one and it makes it curve, it gives off bremsstrahlung radiation, which is this underlying stuff here. And then the bumps on top of that are actually elements, transitions. So if I said that wrong and somebody wants to correct me, that I wouldn't be offended. Okay, so I'm going to go back to my slideshow. So students would zoom in on each one of these peaks. I find it easier to have students take a screenshot. I don't really like the data table. It's easier for me to have like a visual picture like this by the time they're finished, where they have the elements labeled on each of the peaks. So I usually just have them take a screenshot of the graph itself, maybe put it into a Google slideshow. And then as they identify what elements each of these peaks are, just to put the element, just to label the top of it like I have here. Then that way, when they go on to look at other supernova remnants and decide if they're a type 1A or a type 2, they have a more visual picture and can compare the spectra. So this data table, I made this data table from 50 pages of spectral lines from 1 to 10 angstroms from the Chianti database. And I mean, it was 50 pages, a PDF file of 50 pages with lines. And I did not put ionization states on here for each of the elements because with the number of significant figures that we have, and the number of significant figures that students could get for the energy, it just was too hard to differentiate between ionization states. Please notice that these energies are in kilo electron volts. And the ones that you have on your graph are in electron volts. The reason that I left it in kilo electron volts is because this is really as many significant figures as I felt that I could get was to 2 significant figures. I mean, to 2 decimal places with kilo electron volts. So if you zoom in on this big peak here, that is about 1850. So if you divide by 1,000, 1.85. 1.85, the closest thing to 1.85 here would be this silicon line. Students may find peaks on there that are not in my table, but that's just because, like I said, I tried to condense the table from 50 pages of lines. If you have students that, you know, wanted to go to the Chianti database and use all 50 pages and, you know, convert those to electron volts and use Planck's equation and all that stuff, they could if they were advanced enough to do that. Does everybody get the major idea here of how to figure out which elements are in Tycho supernova?
Pamela, there's a question about where to find the table.
The table is in the handout. So on the Chandra site, the activity that we're doing now is X-ray spectroscopy of supernova remnants. So when you look at one of these are the ones that I give my students. So like I was saying, each one of these activities could stand alone. Like I've used this activity in a chemistry class before when we were talking about where elements come from in the periodic table and we're talking about spectroscopy. So it wasn't even in an astronomy class. I showed them like a quick, 10-minute video on the 2 different types of supernova that we were looking at in here, type 1A and type 2. And then I had them identify the elements. So there's a purpose statement. There's background information about Tycho supernova remnant, which is our representative type 1A, and SNR G292 plus 1.8, which is why I always have to look at it and I can never remember the name, which is our representative type 2. Students go through this process that I just explained to you using this table to identify which element corresponds to each of those emission lines in the energy spectra that we were just looking at. Again, this data table, you can have them fill it out if you want to. I really like it, and my students have found it much more useful to actually label the name of the element right on the screenshot of the graph instead of using this data table. So it's up to you if you want them to fill that out or not. Are there any other questions?
So we can just put the pointer on the graph. It shows us the element you are saying, or
Okay, let me go back.
what is the other option to see the element, the name of the element?
This, you have to use this data table to see the name of the element. So you need to get the energy from the graph and then compare that to this data table to figure out what the element is. So I'll show you again.
Art Baker asked if the recording will be available later, and I just wanted to make an announcement to everybody that yes, the recording will be on the Optics website and our YouTube channel. So you'll get a link to that after.
Okay, and I did put the link to my slideshow, which has way more instructions, but I probably put more slides in there than I needed to because I wasn't sure how much we'd be able to get done in the amount of time or what people's interests were. So all of these instructions in this presentation is in the slideshow also, so maybe they could put that up on the Optics site as well.
Yeah, I
It's
can do that.
probably the first link in the chat there.
Yes, I have it up. So thank you very much, Pamela.
Okay, so the question was, how are we figuring out what the elements are? So, for example, if I wanted to know which element this one was, you just drag a box around it, which will zoom in on that particular peak. And then it really bothers me. Sorry, I didn't even think to mention this, but I don't know if it bothers anybody else that they didn't label what the X and Y axis were. They do tell you up here that it's counts versus energy. So this is photon counts, like how many photons hit that particular pixel, or how many photons of this particular energy were collected, I'm sorry. So this on the x-axis, this is energy in electron volts. And the y-axis is number of counts, so the number of photons. So if you looked at this peak, it's about 1850. Divide that by 1,000, 1.85. And then if you look back at that chart, the closest thing to that would be silicon. Did that answer your question?
Yes, thank you.
Okay.
I just
I
thought
have-
if there is an energy that is not in the table, how do we get it?
Because I condensed that table from, like I said, 50 pages, you can either have students leave that one blank. I picked the ones in the table that were most important for being able to differentiate between a type 1A and a type 2. So I would have my students leave it blank. The database that I was talking about is called the Chianti database. So if you have really advanced students, but like I said, I think just 1 to 10 angstroms is close to 50 pages of spectral lines. So they would be doing a lot of searching. I think the other thing that's good to talk about with your students here is significant figures and, you know, how many decimal places am I actually able to get these energies to? If you go to look at the Chianti database, I forget how many decimal places those wavelengths go to, but it's quite a bit more significant figures than we're actually able to get off this graph. And some of the spectral lines can be really close together. So I guess the answer is they can just leave that one blank, or, you know, if they're more advanced and you want to send them to the Chianti database, they could go there. Let them know also, though, that that table is just something that I condensed down to that far, and that I'm not necessarily going to get every single one that you're going to see on every single supernova remnant.
Thank you.
May I ask a question about the Chianti database?
Yes.
Because I don't think I'm familiar with this. It says theoretical line lists and intensity. So these are based on quantum mechanical calculations and not some sort of experimental observations, or?
I don't know. I actually don't know, but this is where I got my lines from. But I wrote this activity so long ago. An atomic database for the spectroscopic diagnostics of astrophysical plasmas. I don't know. It says it's critically evaluated, but I am not sure.
Okay.
Another place that my students have found is the NIST database.
Oh, yeah.
And that allows you to type in values, I think, in wavelengths. It might also have energies, but it's also just humongous. But that one is, I believe, experimental. So, but it's like the Chianti one where there's way more data there than will be useful for a student.
Right, and I think the general idea too is we're not trying to figure out every single element that's in this particular supernova remnant. We're just looking for specific ones that help us differentiate between a type 1A and a type 2. So the idea then is that students would go through and do Tycho's supernova remnant, and then they would go through and do the other one. We probably don't want to go through the whole activity, but does everybody understand the process?
I have another question, if I
Sure.
may. If I have an image of a supernova remnant taken, say, in the optical, will js9 let me analyze it the same way, or does it have to be X-ray data?
No, it depends what's in the FITS file. And I have had issues. I have had issues when I bring in a FITS file from optical, depending on how they set the database up. If you open a FITS file, there's a lot of text and numbers in it, and it kind of depends on what the headers are. And so I honestly don't know like what the algorithm is for this energy spectrum, what header it's actually looking for in the FITS file.
Right.
So I'm not sure.
Okay.
But I do know when I'm going to show you on another activity, there is a way that you can actually bring in optical data and infrared data for this exact X-ray observation, which I'm going to show you in a little bit. Definitely bringing in other FITS files from other missions, you're not going to have all these analysis tools. And the event filter works for a lot of different things too, but you have to know what the table headers are for it to work. Like this one, we knew there was a table header that said energy, and that's why this worked, and it was able to filter out the data.
Okay.
Any other questions? Okay, so I'm kind of giving you the answer here. If you had time to go through the whole activity, but if you look at the two spectra, and this is in a linear scale on the y-axis. I sometimes think that it's easier to see almost with the scale being logarithmic. I can see more of the element bumps. To me, I like looking at it this way better. DS9 used to do it logarithmically by default, and JS9 does it linearly by default. But anyway, so type 1A, you can see this really strong silicon signature here. So strong silicon, sulfur, argon, calcium, iron. I know it doesn't look like there's a strong iron one here. There's also an iron bump here, which you can see more easily when it's logarithmic. And then type 2, you can see this oxygen, neon, magnesium signature at the beginning. Which is what you really want to look at, but you see this oxygen, neon, magnesium signal here is about 1500 electron volts and lower. And sometimes due to interstellar absorption, those are the ones that are actually absorbed and they never actually get to like the Chandra X-ray telescope, and they're completely missing. So the problem is, if you see the oxygen, neon, magnesium signal, you can be pretty sure that it's a type 2. But if it's missing, you don't know if it's missing because it's a type 1A or it's missing because those were absorbed and it never even actually got there. So there are other things you can look at. I don't know if you remember before when I was sliding my mouse back and forth and up and down to change contrast and bias. I know it's probably hard to see on your screen, but this is the one that we were just looking at. This is the one that we didn't do, that's our type 2. If you play around with the scales and contrast and bias, there is actually a little bright white dot in the middle, that could be the pulsar or neutron star at the center. You won't find something like that in a type 1A because the white dwarf is completely destroyed when it's supernovas, so there's not going to be a core remnant. Whereas a type 2, there, if you don't see that neon oxygen magnesium signal, you can also look to see if there's like a core remnant in the center to help decide if it might be a type 2. Are there any questions there?
Can you show us how do you get to see if there is a core under the analysis, I'm guessing?
Sure. The one thing, just with the default image that comes up, Cas A actually is a type 2. And can you see the tiny white dot where my cursor is right there in the middle?
Yeah.
But you can also change, if I change contrast and bias, do you see how I can see it even better?
Yeah.
And you could also try different scales. Squared doesn't help. It's a little bit more obvious with linear. You can see the dot in the center. The square root also is a good one to help me see the dot in the center. And again, like changing contrast and bias could help you to see it. They're small though. So this is the one we didn't look at, but you can actually play around with that one and you do see it. This one though does have a very strong oxygen neon magnesium signal. So we have these two that we're kind of using as our guides. And I like, again, to have the students put the elements right on the graph so that they have more of a visual. So logarithmically, this was my type 1A Tychos. This was my type 2. With Cas A, do you see how this, if you looked at these peaks, you would see the oxygen neon magnesium, but do you see how it's not as pronounced as it is in this one? But we do have our core remnant here. Again, when I'm having students do this, if a student, I mean, obviously they're doing supernova remnants that have been studied before, so it's not like they can't Google if it's a type 1A or a type 2. I mean, I try to tell them not to, but it's hard not to see when you're picking your supernova that you want to do your project on. But if a student's reasoning is sound and they say, I think it's a type 1A because, and their reasoning is sound, but this signal was missing at the beginning, as long as I'm not so much concerned about complete right answers as I am about them being able to explain their reasoning for why they said something is a type 1A or a type 2.
Bingo.
Does anybody need a break? I can keep going.
Shall we take like a 5-minute break just to rest our eyes? And
That sounds good to me.
so we'll meet back at 25 past the hour.
Okay.
Okay.
I will pause the recording.
So you asked about how I got involved with this. I went to an astrobiology conference back at Bowdoin College, which is where I went to school, and I live down the street from it now, and met Donna Young. So she was in charge of education public outreach for the Chandra X-ray Observatory, and I just started working with her, and somehow I ended up being the one that I guess DS9 kind of caught my fancy and I started writing activities for it and then just kept going with it. And she's great because she doesn't say write a JS9 activity on such and such a thing. I always got to pick what I was interested in. So this leads into the next thing that I was going to say. All of these activities, I wrote these activities. The thing that I did not write that's on the website is there are guides for using JS9. You don't need to use those guides to be able to do any of these activities. The activities are all step by step, like, go to this menu, this choice, etc. The instructions are written out so that you don't need to look at the guides, but the guides are there, especially if students are going back to do their own research projects. They might want to look at stuff in the guides. There's some tools that maybe I didn't hit in one of the activities that are mentioned in these guides here. So they're there, but you don't need them to do the activities. Terry Matilsky from Rutgers University, who keeps a good eye on JS9 and the developments and everything for us, wrote those two guides. And actually, I think it was a long time ago, was one of his 2-week workshops that I went to at Rutgers, where he was doing stuff with DS9 that got me writing these activities. So when I'm writing these activities, a lot of times the places where I got my inspiration from was going to just the Chandra X-ray Observatory site, which is the same site that this is hosted on without the JS9 extension on it. And just looking at the photo album here and looking at the most current thing, when you click on one of these, you can do them by categories. So if you were interested in supernova, you can click on a supernova. Down at the bottom of one of these, there's a fast facts page, and these are all the different observations of this particular object. So if you remember where we clicked the unofficial Chandra archive search and we typed in the number 115, that was an observation ID number, which you can get from here. So some of them I just looked at these objects and they seemed interesting, or the story seemed interesting. And then, let me go back to my slideshow presentation. So I might have seen this picture that just looked beautiful to me with the observation ID number under it, and started reading about these colliding galaxies and how it was looked at in different bands of the electromagnetic spectrum, and then wondering if this could translate into an activity for students. And so then I would go back and find the scientific paper that used that observation and kind of backwards engineer it into something that I thought my students could understand. So, they are actually doing the activity and going through the process the same way, but obviously I'm kind of like leading them through the steps towards a certain understanding, I'm hoping, by the end of it. And also I was trying to pick activities that each one of the activities teaching a different tool. Like you did the 3-color composite, you used the event filter, you did spectroscopy where you used an energy spectrum. The one thing that I really like about this activity, the Cartwheel Galaxy activity, is that it uses X-ray data and it also uses energy from the visible range of the spectrum. We're not going to do this, but just kind of as an aside, I will show you how to pull in data from another mission in a minute, but you can also do 3-color composites using data from other missions. So if I made the X-ray information blue and I made the infrared information red and I made the visible information green, you can also make 3-color composites that way too. So they can also be from different missions. Okay. So the idea on this particular activity, the Cartwheel Galaxy activity, is this is very small. Let me make this bigger here. Up in the corner here, this is what the X-ray data looks like for the Cartwheel Galaxy, and you can see all these really bright X-ray sources. And the idea of this activity is, what actually are these objects? I think one of the things that students really don't understand is that what we know about the universe is from the light that reaches us. And when you open something in, you're going to laugh when you open the X-ray data in js9. You just look at it and you see a bunch of dots, and each dot is maybe like 2 pixels big. And how do astronomers actually know what that object is when they have 2 pixels of data? How do they figure out what it is? So the unusual shape of the Cartwheel galaxy is likely due to collision with one of the small galaxies on the lower left several 100 million years ago. The smaller galaxy produced compression waves in the gas of the Cartwheel as it plunged through it. These compression waves trigger bursts of star formation. So the idea of this is that we're going to pull up the X-ray data, and we're going to pull up the optical data. And a really cool feature is that you can put crosshairs on here, and you can sync the crosshairs so that as I move the crosshairs over this image, they'll move over here. So first of all, it helps you to see, like, these X-ray sources. You can sync these 2 images together so that you can see where these X-ray sources correspond to the optical data. And I'm going to show you how to do all this stuff in a moment. But just to give you the overall idea of what we're doing here. And then we can also, on the optical data, we could get the size of the Cartwheel's ring, and using the small angle formula and the distance and an expansion rate, which is found by another method, and I don't actually know what the method is unless they've, observed the Cartwheel galaxy over time. I don't know how they know the expansion rate is 200,000 miles per hour, but they must have gotten that from some other data. So just, students would have to know that. But if you know how big the Cartwheel galaxy is and you know the expansion rate, you could figure out how long ago the other galaxy kind of plowed through this and started star formation. And then once you know that, you can then say, okay, well, if it happened this long ago, and we know certain things about the life cycles of stars, like how long does it take a massive star to go from star formation to something that would be bright in X-rays, like a supernova or a neutron star or a black hole. That kind of information could then help you figure out what those X-ray sources are. So that activity also, the one I'm looking at now, I'm having a hard time scrolling here. It's just the Cartwheel galaxy activity. So I think the main takeaway as far as new tools that you can use in js9 with the Cartwheel galaxy. So first of all, I'm going to close this image out. I'm going to go to the unofficial Chandra archive search page. You actually can type Cartwheel for object name. You'll get a bunch of different observations. I think the one that I'm going to look at is 2019. But you could also type Cartwheel galaxy for object name and a bunch of observations would come up. Let me just show you what happens when you do that, instead of putting in the observation ID number. You can see exposure times right here. So observation 2019, it was 76.1. Exposure time is in, now I don't know, seconds.
says kiloseconds. Just
I was
above
gonna
there.
say seconds didn't seem long enough. It would look at it for longer than a minute. Where does it say kiloseconds?
Right above
Oh,
there
okay.
under
Yeah, that makes way more sense than seconds. That would be a really short observation.
Sorry,
So-
can you please remind us how you search by name?
I just typed Cartwheel Galaxy in where it says name.
But how did you get the window to type in? Where did you click on?
Where did this window come from?
Yes.
The unofficial Chandra archive search page. Right here.
Thank you.
Mhm. So this one is the longer exposure time, so that's the one I'm going to use. So I'm just dragging where it says the cartwheels ring, just like we did before, drag it over here and drop it in. And you can see how impressed your students are going to be with this data. Isn't it pretty?
I'm sorry, which one of those did you drag over there?
I dragged over the one that says the cartwheels ring because it was the longest exposure time.
Okay, got it.
So that was sarcasm?
It was
Seeing-
total sarcasm.
Awesome.
Yeah. No, so under scale, first of all, I would pick log. And this is still, it's still awful, isn't it? But I would also, this is actually it right here in the instructions. I think I tell the students to zoom in, go to Zoom 4. Isn't it still awful? They always are like big on picking colors, so I just randomly picked cool, but it does, the colors don't change the data. If you don't want all that background stuff, you can change the contrast, just slide back and forth and change the contrast and bias if you want to get rid of some of that background stuff. Again, none of this changes the underlying data, so you don't have to. So I'm using a trackpad. I don't know if you guys are using a mouse, but I'm just, I guess it's called a right click. You can either slide this way or you can slide this way and change contrast and bias.
Mhm. Lordy, if this had been available 35 years ago.
So these really bright things are what we're asking the question about. What are those X-ray objects that are so bright? This is the question that the students are trying to answer. And I mean, look at this one. This one right here is what? It's like 1, 2, 3, 4, 5 pixels. And how do they know what anything is from 5 pixels? Does everybody have the Cartwheel Galaxy up? The X-ray data? No questions in the chat that I can't see?
I have the X-ray data, but I don't have your picture. How did you get from 2 dots to this?
I don't know if you changed the zoom to 4.
But did you click on something before changing the zoom to
Well,
4?
do you have it on Zoom 4?
Yes, but my picture is.
Okay, and then do you have scale log?
Oh, I got it. Thank you.
Okay. Yeah, look, it doesn't look like anything under linear, right? I know that's what, all this is in the instructions, because when, just students come up and it's just a blank screen there, they just think something went wrong and they don't realize there's actually data under there. Okay, now this is really cool. This is like my favorite part of this whole activity and why I decided to do this one next, even though usually I do this one after this one when I do. This is actually the order that I do these in my class, the way that they're listed on the website too. All right. So now we want to pull the optical data in. and put it side by side. So we're gonna go to, if you're in the instructions, we're on step 4 where it says acquiring the optical image, but you're gonna go to view. Archives and catalogs. And there are a lot of different servers here. This particular one, the default one that comes up will give us optical data back. There's this one here, you can see it says IR next to it, gives us IR data, infrared data. But the default one that comes up, so we're view, archives and catalogs. This one will give us the optical data. You need to hit the button that says set right ascension and declination. So that retrieves the location from the FITS file that we already have up. And then it's going to search in that catalog to find optical data in the same location. And so you just go get data. And again, I'm going to hit, it's tiny. So again, I'm going to hit zoom 4. Black and white's boring. So I'll pick a color. Does anybody need help with this step? Okay, and then obviously it's not too useful if we're trying to figure out the location of the X-ray objects if the image is underneath. So you go to File and Separate. Separate these images to put them side by side.
So if they are on the same scale, are they the same scale on the x-axis and y-axis? The two correspond to the same picture?
We're gonna line them up in a second. So we're gonna reproject them to make sure that they are the same scale. Okay, so we wanna, that was a good question because that was our next step. So on the optical image, where it says WCS, we're going to do WCS reproject. This is the only other image that we have open. So WCS, WCS reproject, and then this is the name of the X-ray image right here. You just click it and it lines it up so now they are the same scale. Do you see how it shrunk just a tiny bit? Okay, and then we're going to put crosshairs on both. So we're going to go to View, Show, Crosshairs. They won't show up. Okay, now, before you do this, I did View, Show Crosshairs, and the crosshairs didn't pop right up. Don't, don't right click because we don't want to change the contrast and bias. but you have to hold the shift button down, and when you hold the shift button down, the crosshairs will pop up. I can show you again over here too, on the other image. So view, show, crosshairs for this image. And you notice they aren't there, but I hold the shift button down and I just move the mouse and the crosshairs pop up. So I'm holding, if you try to move the crosshairs without the shift button down, they don't move. But I just have one finger on my trackpad when I'm doing this. Students will accidentally, they're so used to right clicking on everything that they'll start dragging stuff around and they'll change the contrast and bias and mess everything up. If they do, you can just go to color and reset contrast and bias right here so that it resets it if they mess it up by accidentally right clicking and dragging. Once you have the crosshairs on the two images, if you then go to view, show, and match crosshairs, now when I move them, they move together. Isn't that cool?
That's amazing.
So, I mean, what I love about this activity is we pulled the X-ray data up, then we were automatically able to pull the optical data up. We were able to resize them so they were both at the same scale and reproject them. And then in trying to figure out where these are, you can see that they're on the ring of the Cartwheel Galaxy. I mean, you saw what these two images looked like before we did any of this stuff, that wouldn't have been immediately obvious that that's where these X-ray sources were located. Then there's some like X-ray sources over here, and it's kind of interesting to see where those are located too. This one doesn't seem to like have an optical source like in the field. This one's over here, but these two. Does anybody have any questions on the crosshairs? Again, if you are having problems with this, you've kind of at least seen what this does. So later on, when you can get to a printer or whatever and print the instructions out and then go through it yourself to practice, it might be easier. So, you know, one of the first questions that you ask students is just, where are these X-ray sources located on the Cartwheel Galaxy? And you can see that they're located on this outer ring. And then we have used the region tool before. If we want to know how big the Cartwheel Galaxy is, it's a lot easier to see it on the optical image than it is to see it on the X-ray image. So if you did a region, a circular region, and drag it out so that it's about the size of the Cartwheel Galaxy and move it around.
Pamela,
So I just did region circle,
yeah, I'm not seeing the screen.
my screen.
Oh, odd. I'm seeing it, Tom.
Okay,
Well, that makes it difficult. If you go to regions list, it gives you this information here that I highlighted in blue. That's in arc seconds. That is the radius of the region in arc seconds. So without going through all the math is explained in the handout. You can take a look at it later. But the idea here is that they get the radius of the galaxy. Using the small angle formula, they can figure out how big what the radius of the galaxy is in miles. And the only reason that they're figuring out what the radius of the galaxy is in miles is because in the background information to this, it said that it was expanding at 200,000 miles an hour, I think. So I'll just run through the rest of kind of what the analysis was just by using my slides without making you guys do math right now. So once you have the radius in arc seconds and you convert it to radians and you know how far away it is, on the Chandra photo album in the fast facts section, where I found the observation ID number, it also tells you how far away it is. So using the small angle formula, they could figure out how big a cross this was in miles per hour. So you can get them to practice some dimensional analysis here. And if they know the expansion rate, which was in the background information in this handout, then they could figure out when the smaller galaxy collided with the cartwheel. So if that was about 300 million years ago, if you do all the calculations, and you know anything about the life cycle of stars, and there is a table in the handout that some representative lifetimes for other stars are given in the table below. So in the handout, there is a table, and it says that blue-white stars have a lifetime of about 370 million years. It says that in the table. So 300 million years is enough time for, if when the two galaxies collided, new star formation started, that 300 million years is enough time for some of those massive stars to have gotten to the point where they have supernovaed and become black holes and neutron stars, which are very energetic things that would definitely be very luminous in X-rays. Are there any questions? Is anybody's brain ready to explode yet?
I cannot get the size of the area, the circle.
If you make this region around it, I'll go back to my screen here. So I'll take it back off again. If you go to region, circle, I dragged the circle out so it was about the size of the Cartwheel Galaxy. And when you go to region list, this information comes up here. This is the right ascension and declination of the center of the region that I just highlighted. And this last number here is the radius of that region in arc seconds.
All right, thanks. I'll try.
So I have well, I'm not a classroom teacher this year, but it's my first year out. I've been teaching since a classroom teacher since 1988. This is my first year doing something different. But one of these activities, we have 70-minute periods. And when the students have the instructions right in front of them, I start off with the 3-color composites activity first because it's a lot simpler. The X-ray spectroscopy one is usually the one that I do second, but I'm usually able to pretty much get through one of these activities in a 70-minute period with high school students. Are you all set on the size?
Yes, I got the size. Mine is 40 arcsecond.
Yeah, I mean, we're just getting an approximate thing anyway. We're just,
Yeah.
you don't need an exact time. We're just trying to get an approximate time. And
Can,
definitely
can
it
you
has to do with,
show where
say
to
that
go
again?
to find what is the distance to this galaxy?
In my handout, it's in the background information that I have at the beginning of the exercise.
Okay.
But also I'm not clicking on the Cartwheel Galaxy, I'm just clicking on a random one, but in the Chandra photo album, not this one, figures, right? Usually I can get usually the distance is in the fast facts here too. But it's also something that you can Google, like how far away is the Cartwheel Galaxy? But
Thanks.
it is in the background information that goes with this activity also. A lot of times it will be in the fast facts section on in the photo album here. So if I search Cartwheel Galaxy and found a photo of the Cartwheel Galaxy, or in the photo album, sorry. Also, I think I mentioned before that I had a scientific paper that I was backwards engineering this from too, so I knew some of these things from reading that. So I gave the students some information also from that I had gotten from my research. So one of the other questions that you can ask about this same thing, since we had those crosshairs up, is we had those X-ray sources that were along the kind of wheel of the Cartwheel Galaxy, is talking about an active galactic nuclei, which produces, in some galaxies, produces more radiation than the entire rest of the galaxy. So first of all, so if it's that energetic, it should be a very bright spot in X-rays. So first of all, see what I just did? That's what the students do all the time. I didn't put the shift key down and I just started dragging. So you can reset it again, reset contrast and bias. So holding the shift key down and then just, does the Cartwheel Galaxy have an active galactic nuclei, would you say? So in other words, is there in the center of the Cartwheel Galaxy, do you see a corresponding bright X-ray source?
No.
Okay, but are there some other galaxies in here that might have an active galactic nuclei? So students can kind of see where are these other X-ray sources? What do they correspond to on this? And this little thing here, the picture is flipped upside down from the one that I had on my slide, but they're thinking that it's one of these two galaxies here is the one that plowed through the Cartwheel Galaxy. You can see this galaxy right here does have an active galactic nuclei. There's a really bright X-ray spot in the middle of that one. One of the coolest things about this activity is, here's my PowerPoint. So I'm not an astrophysicist, and when I was reading that scientific paper to put this activity together, first of all, I'm lucky because I have Terry Matilsky, who's an astrophysicist. So whenever I write one of these, I'm always afraid that when I summarize, summarize in a way that makes something misleading. So I'm really lucky that I have him to proofread for me. You know, I think I'm really good at making instructions that high school students can understand and get through. But I'm always worried that when I summarize things that it makes my science sound wrong. So he proofreads them for me. But one thing that I really like about this activity is even when I sent students back to the original scientific paper, they're not going to probably understand 90% of what that paper is, but there's some really good diagrams. And without me telling them what the answer is, when they go back and look at the scientific paper and they compare what they think that those X-ray sources were with what it says in that paper, if they're willing to kind of comb through it, they're always like really, really excited that they took real data and it came up with similar answers to what the astrophysicists came up with for what those X-ray sources are. So I just have to like try to be really quiet about what the answers are. You know, and not say, oh, you got that wrong, you know, that's not right. That's I want them to do the analysis and then kind of compare what their analysis is with what the analysis is in this paper. And they do understand enough to be able to find the parts of the paper that kind of match up with what they say. So the activity is a little contrived because I was trying to lead them towards those answers. But also they think of all the different tools that you've learned just in this one activity, how to bring data up from 2 different missions, how to line the data up, how to put the crosshairs up, you know, how to measure how big something is by using a region. So you could use it just to talk about what happens when galaxies collide, or it's also a piece that shows them more tools that js9 has that they could use in their own research. Are there any questions? So we have about an hour left, and there are some different, from reading what you had said ahead of time, it seemed like there were some different ideas about what you wanted to get from it. One of them is, I just wanted to really quickly, I forgot to say something on the, oh, I guess I left it out. I have like a million slides here and then I left one out. What I wanted to say was on the spectroscopy one that we did, if you want students to look at some supernova their own and classify them as type 1A or type 2, I kind of vetted a bunch of them. If you look at some of the supernova, they look so cool in the Chandra photo album. And then when you pull the data up, students end up looking at a supernova remnant that has like 10 pixels and it's like super boring. So I did kind of vet some supernova. So I did at the end of that activity give some choices of OBS ID ones where you get a lot of pixels and they're kind of cool to look at. I had students, when I had them do their, at the end, I had them do an Adopt a Supernova project. And what they had to do in the project was make a 3-color composite. They had to decide if it was a type 1A or a type 2. I think I had them do some other things, like one thing that you can do is combine what we did with the event filter on the 3-color composite activity. And you could look at element distribution if you wanted to. So what I did on this was I knew what energies silicon was at from that table. And I used an event filter to say, I only want to see this very small range where around the energy of silicon so that I could map out where the silicon was in the supernova remnant. You know, this supernova has some weird features, like you can see this jet out the side. So, you know, what element is that made up of? So students could do things like that. students could also do 3-color composites from different bands of the electromagnetic spectrum rather than a 3-color composite just from X-rays. So there's all sorts of different tools that they have. I gave students lots of different databases where they could look for the supernova that they wanted to do. And then some kids absolutely refused to use any of the ones that were on my list because they wanted to make sure they had a supernova that nobody else had. And they were willing to spend an hour loading in all sorts of different OBS ID numbers until they found one that looked cool because they refused to do one of mine. And then some students did not have that much patience and they just picked one off my list that I had kind of vetted for them that I knew would be good ones to do for their projects. So there are several more activities, and I also know that some of you were interested in where you can get more FITS files to put into js9 for research projects. The other activities that we have not done yet, I wanted to give you an example at least of a couple and have you go through just to see how the steps are laid out. So we did making 3-color composites, analyzing energy spectra. We just did the Cartwheel Galaxy one. This one is great for a physics class. I just want to show you the pictures really quickly first on this one. So I'm going to jump ahead. If you look at this image right here, and then you look at this image right here, if you're a high school student and you look at those two things, you understanding how scientists would know that one is a white dwarf and one is a neutron star is actually, well, to me, it's pretty mind-blowing. I mean, maybe they take it to kind of take it for granted, but those two things look very similar. And so what this activity does is it looks at light curves. And so if you think about a hot spot being on a star and having it rotate kind of like a lighthouse, and as it rotates, that bright spot rotates in and out of view. If you did a light curve over time, you would see the intensity of the light increasing when that hot spot rotates towards you and decreasing when it rotates away from you. So with a light curve, you can actually figure out the spin rate. And by figuring out how fast it spins, you can do a bunch of calculations with centripetal acceleration and Newton's universal law of gravitation and how big a white dwarf is and how massive and how big a neutron star is and how massive. And you can figure out by the spin rate if it's maybe a white dwarf or maybe a neutron star. Neutron stars have a lot more large gravitational field than a white dwarf. So a neutron star can spin a lot faster than a white dwarf can. If a white dwarf were spinning as fast as a neutron star, it wouldn't be able to hold together. So that's one of the other activities. There's also an activity where you actually look at the expansion rate of a supernova remnant. So you're actually looking at data from 2 different Chandra observations over time and figuring out how much it's expanded. I had to go to this database right here is where I actually found 2 observations that were 10 years apart that had the same right ascension and declination, so that I had 2 observations. So just like you separated the X-ray data and the optical data for the Cartwheel Galaxy, I put up an observation of Cas-A from 2004 and an observation of Cas-A from 2014 side by side and made sure that they were lined up. And the same way that I measured the size of the Cartwheel Galaxy by using a circular region, I kind of measured where these observable parts, how much they had moved, set up a whole huge giant, I guess I think I set up a spreadsheet where I could, figure out how far they had moved and translate that, knowing how far away it was to how far it moved in kilometers and actually calculate the expansion rate. And then there's a brand new one that is actually looking at the bullet cluster in various areas of the electromagnetic spectrum to look for dark matter. So at this point, I would imagine people are probably kind of tired of using activities, and I want to make sure that you have a chance to ask questions. Some people were interested on where you can get more data, your own data, to be able to bring into js9, so be able to bring in your own FITS files. So I want to pause and see what kinds of questions you have at this point. Or where you would like to go for the next 45 minutes. We can do another activity. You guys can ask me questions. I can show you other databases.
Okay, so I'm looking at the cartwheel handout, and it's
Okay.
asking a few questions, right? You asked us to. There is no answers, like there is no teacher guide, but you say they can find all the answers in those papers that you're citing. So
Actually,
they
it answers at the very end. So if you don't link your students to the handout,
oh, I
because
can
it's the
see
answers
the
at the end.
mm-hmm. Cool. Okay.
So print it out. Oh, yeah, it's sitting right there too. They're probably going to click on it and find it, but there is answers at the end.
All right. All right. Thank you.
And we have a question in the chat. What other databases do you recommend?
Okay, so this database here, and you guys have a link to the slides. I know that that's a long URL. So first of all, as far as if you want X-ray data, using the Chandra photo album, you can sort by categories. So if you're interested in supernova, and you can also do searches up here too. I was trying to find one that I know. So if you look at if you click on a particular supernova, hopefully I clicked on one that has good fast facts. Down at the bottom here, you will see observation ID numbers. So this is one way of getting more X-ray data, because you can then take any of these observation ID numbers and you can put them into the unofficial Chandra archive search page. You can put the observation ID number there, or you can put the object's name in there. So that's one way of getting X-ray data, is by using this search page, either of those two ways, which are two ways that we've done already. So does that part make sense to everybody? And if you have the X-ray data, you can also, using view and archives and catalogs, like if you wanted infrared data for the same observation, you can get that this way through the archive and catalog that's built right into js9. This database right here, let me just show you what this mission interface looks like. So if you go to browse mission interface. And again, this link is in the slides. So you can go back and get it later. So this is a great place to get FITS files here. You can put the object name in here. So you could type in Cartwheel Galaxy. You can type in the right ascension and declination in here. You can pick by mission. So it tells you these are X-ray missions, gamma ray missions, etc. So you can pick by mission. I guess I must have typed Cartwheel Galaxy in there before. So you can pick multiple missions if you want. Start search. Sometimes this takes a little while here. Once you do the start search, it says data products retrieval up in this corner. I have this in one of my other slides, and I'm not sure if I have it in this PowerPoint, but I'll make sure that the slide that has this process on it gets put in if I left it out of this slide presentation. It takes a little while sometimes. I'm gonna be mad if I like picked something that actually doesn't have any products. I might have, but you click data products retrieval. Oh, there it is. Nope. I'll go back. I'll pick another mission too. Oops, that's not. I'm sorry. I guess either the Wi-Fi is slow here because I'm in a public library, or I'm not giving you the process right, but I will definitely make sure that I have the slide in there that explains how to use this database. But you can see that there's a lot of different missions here, and you can get a lot of FITS files from this one database. So I'll make sure that I make that slide's in the presentation, so you have those instructions. Are there any other questions? So at the end too, I had a summary here, so you can get ideas for research projects from scientific papers. Again, sometimes I just go to the regular Chandra's site, and if something, they might have like news on the front page, and that piques my interest, and then I go, you click that link, and I go to the fast facts, and I get the observation ID number, and I pull it up and just start playing with the tools in js9 to see what I can do with that particular image. Oh, the micro observatory is also a really cool one. I don't know if you've seen this one. This is also in the slide. But if you go here, students actually, I don't know why this is so cool, because it's not like I can't look up and see the moon from my house, but I went to the micro observatory website, and you go to observing with NASA and control the telescope. And if you follow the prompts there, you can select a target in the telescope settings, and then as soon as a telescope in their network is able to look at that particular object for you, then you get a FITS file in your email, and then you can upload it to js9. So I had asked it for an image of the moon. And in that FITS file, you can't do a lot of the analysis, but at least you could. It was my picture, which I thought was cool, and I think the students would find cool. And then I was able to bring it into js9. And the things that I could do was I could zoom in and on, I could change the scale, I could change the color. So that's kind of an interesting website also, where students could actually pick the object and then get their own FITS file sent to them in email. You, again, with this moon one, there wasn't a lot I could do with the analysis tools with that FITS file. If I were to suggest something else, one of the other really big tools is in this activity that I was talking about here. Figuring out the difference between which of these objects is a white dwarf and which one is a neutron star. One of the tools that we haven't looked at yet is a light curve. So if you were interested in trying that, while I'm still here to help. That exercise is analysis of 2 pulsating X-ray sources.
So how about this? Shall we officially end the workshop and then stick around to have some playtime?
That would be fine with me. I know that this has been a lot to go through all these activities in this amount of time. So I was just kind of trying to judge how tired people were. If they were wanting to do one more, or, maybe some people do and some people don't. So that's why I was trying to get feedback.
I'm highly biased, but I'm wide awake.
Okay. Well, I mean, the light curve one, I really think the light curve one is definitely, if you do the 3 that we've done so far, and then you do this particular one with the light curves, I think those 4 activities are the ones that give students the most tools to be able to use when they're doing their own research projects. So I'm happy to go through that one.
I can stay for that one too.
Okay.
I want to see it.
Okay. I am going to paste a link in chat for you. We're going to cheat, and we're going to go to a website that has CenX3 and GKPer already preloaded, where we can just click on it, and it saves us some time because it already has some regions drawn on it to capture some photons that got scattered by some of the instruments in Chandra. So I'm going to paste this into chat first so that you guys can get there. Uh-oh, I only sent it to one person. I didn't send it to everybody, I don't think. All right, let me try this again. There.
Yeah, I see what you see when I click on that link.
Okay, let's do GKPer first. So we're going to click on this one. And I actually don't know, there's something to do with the diffraction gratings and stuff like that, is what these artifacts here. And Terry Matilsky is the one that drew these regions around. And the reason that he did that is because he wanted to make sure he captured all this information that was here too, but these aren't like jets or anything that's coming off here. This is due to the Chandra instrumentation that's making these things come off this way. Okay, so we're making a light curve because we're trying to figure out what the rotation rate is here. So you want to go to analysis, and there are two places for light curves, but you want to go under NSO analysis. Don't do the light curve here, do the light curve here. So under NSO analysis, you want to hit light curve.
I'm just curious. Light curve is a function of time. So in one image, how can you get a light curve?
Because it's looking at it over a period of time. It's not a single snapshot. It has, remember that we were talking about the exposure time before?
Ah, okay. So that's embedded in the FITS file,
Yes.
that second by
Yeah,
second,
so,
or that moment by moment. Okay.
right.
All right.
So when a photon comes into Chandra, it records the energy, the location, and the time of arrival.
Okay.
And look
Gotcha.
at, it's a graph that actually has the X and Y axes labeled. Unlike the other one.
Yay.
Okay, so first of all, this isn't the only way they're going to be able to get the period of the light curve, but you can see this is a mess, right? I mean, trying to figure out to any degree of accuracy how often this repeats itself is difficult, but you can keep zooming in. So if you drag a box, you can keep zooming in and keep zooming in and keep zooming in and keep zooming in until at some point you can maybe start to see this regular variation.
So this is kind of a geeky question,
Yep.
but does js9 have a way to take this data and do a Fourier transform?
Yes.
Ooh.
I was just thinking the same thing, Chris.
You have to do this light curve first, but then you can. So you could just have students keep coming in and then saying, well, how much time is it from one peak to the next peak? And get the period of rotation that way. Is everybody with me there? Or
Yes.
after you, go ahead. I don't want to talk over the question.
I was just saying yes. I'm there.
Okay. Once you've done the light curve, you have to do the light curve first or it won't work. Then you can do a power spectrum. So this is telling you the frequencies that show up the most often. Am I saying that right?
I believe so.
Okay. And you can, why is it like, luckily I can go back to my original one. You can keep zooming in on the highest peak here. I don't have a calculator in front of me, but I have one on my computer. So this is giving us frequency, not seconds. So what would you say the frequency is of this peak right here about?
Point 0025.
Did you say 285?
285.
And then so if I flip that over, that's about 351 seconds. So another really cool thing, that's actually probably good enough to know that it's about 350 seconds. Another really cool thing is period folding. So this one's a hard one for me to explain to my students, but if they know anything about like destructive and constructive interference when you're talking about waves, if you like added two waves together that were slightly out of sync, they're gonna kind of cancel each other out. So period folding would be like if you had a wave and you kind of cut it into what you thought were wavelengths and then tried to paste them one on top of each other and add them together. If you have the period right, you would get, I'll just show you. Well, so I said 351 seconds from that. Let's say I try 349 seconds and do a period fold. Hopefully it comes up. Or maybe it's not going to come up. I think I have a picture on my slide too. Let me just show you that's faster. I tried 357 seconds and it looked like this. I tried 345 seconds and it looked like this. And I tried 351 seconds and it looked like this. So that kind of helped me zoom in, but I don't know that the period fold is necessary. I think just the power spectrum is good enough.
So it's almost like there's a resonance there when you pick a correct period and you look for the
Yes,
resonance in that graph there.
yes.
Okay.
So why don't you try where am I even now? Why don't you guys try close this file out. And we just did GK per. Why don't you guys see if you can tell me what you think the period of SenX3 is? Using the same process that we just used. And if anybody needs any help with that, just let me know. If you don't forget that when you pick the light curve initially, don't forget to use the NSO analysis tools and not the server side analysis tools.
What's the difference between those?
I don't know. No, I really don't know. I mean, because we use the energy spectrum one before under server side analysis. I don't know what the light curve is doing under that one. All I know is that if I do this light curve, I have to do this light curve, I know, before I can do a power spectrum, and I know that doing this light curve before does not let me do a power spectrum afterwards.
Ah,
So but I don't know.
curious. And I have
I mean,
another
I
question.
don't even know why light curve is there in both places, so.
So while folks are working on this, I'm curious, was JS9 created for astrophysicists? And now you're creating educational tools? Or
I mean, yes, js9 is used by astrophysicists, and I don't know if they use the exact same version as the one that's on the National Science Olympiad. I mean, I would think just at looking at things like significant figures and things that we've talked about so far, that they would need a tool that was a little bit more precise or powerful, but I know every time they make an update, there's all these astrophysicists on the thread, like talking back and forth, going, no, it needs to do this. No, it needs to do this, or this isn't working right. So I know that they're using it. Yes.
very cool.
And there's, over the years, it's been funny too, like people getting upset when they change the scale on axes or don't label them or all sorts of stuff like that on graphs too. That's been kind of funny. But there have been many, many updates. So there's definitely, it's not a stale thing. They were doing updates right before AAPT when we had the 4-hour class this summer, and Terry Matilsky was like, don't update it yet, because if you break it, Pam's gonna be in trouble. So he made them wait until I was done to
Aw,
update it.
you have the power.
Yes, so
So is the period something like 4 or 5 seconds for this Gen X3?
what did anybody else get a number?
I got 4.8.
Okay. It sounds like you guys are in the same ballpark then.
Mm-hmm.
So that's a pretty big difference between something, first of all, something spinning once every 351 seconds seemed fast to me, but can you imagine something spinning once every 5 seconds? So then the tail end of that would be then to now that we know the period and the spin rate, to compare centripetal and gravitational acceleration. So if you took typical masses of a white dwarf and a neutron star and a typical radius, you could find the acceleration due to gravity on the surface using Newton's universal law of gravitation. So this is one that I've done in my physics classes before. Just give them some quick background information on what a white dwarf actually is and what a neutron star actually is. And then when we're doing Newton's universal law of gravitation, I actually have them calculate the acceleration due to gravity on the surface of both of these kind of objects, given the typical mass and radius. And then I have them use the spin periods that they get from the light curves to find the centripetal acceleration on the material on the surface, and have them do the calculation for both of them, pretending that it's a white dwarf or a neutron star. And so if the centripetal acceleration is less than the acceleration due to gravity, then gravitational force would be enough to hold it together without disruption. And if not, and it's spinning too fast, so just from these two, which would you say was the white dwarf and which would you say was the neutron star?
The fast one is the neutron star.
Yes, yes, because that it's isn't it crazy how small neutron stars are? I mean, I'm looking at that thing and it's like, how massive they are, but then with a radius of 10 kilometers, how dense that must be. It's pretty crazy. So here's the whole calculations done out where they're comparing these two numbers. So they only need to calculate the acceleration due to gravity using Newton's universal law of gravitation. They just need to do it once for each of these. And then given the spin period, they can try the 351 seconds in here. And then try the radius of a white dwarf or a neutron star, and then they can put the 5 seconds in and try the same thing, and then compare this number to what they got from Newton's universal law of gravitation.
Yeah, thank you. This is super helpful. I've been looking for something like this for my IB classes. It seems like everything that you do, I can use it as well. Maybe not even everything. It's a lot that you have presented.
Yeah,
Thank you.
it's a lot. Oh, you're welcome. So there are a couple more that we didn't do. I showed you the expansion rate of a supernova remnant really quickly already today. The one thing that's cool about the expansion rate of a supernova is different parts of the supernova remnant don't even expand at the same rate. So it's kind of interesting to look at how are these pieces in the outer edge, what's the expansion rate here? And then comparing that to some historical sightings that could correspond to was the Cassia supernova remnant actually seen on Earth when it happened. So there's some interesting background information and some history. And then you can actually, so that was the outer shock wave. Then you could actually like look at the inner shock wave and see if that's doing the same thing as the outer shock wave. You can, I guess I don't have this slide in. You can also look at the jets and see how the jets are changing over time. So there's all sorts of different things you can do with that. This one is frustrating. So I definitely think that this is one of the harder ones. It's really not necessary. It doesn't teach you that many new tools, but if you really want to get into the physics of what's happening with the supernova remnant, it's pretty cool. It is hard though. You guys tried putting regions on there, and you could see that when we put a region on for the Cartwheel Galaxy that we weren't getting all the exact same numbers for the radius. So one thing that I would suggest is if students are like, say you wanted to figure out how much this little piece right here moved over time. A class spreadsheet is a really cool thing because the more data you have, the more data you have, the better your answers are going to kind of be. So setting up a whole spreadsheet of data to put in that does the calculations for you to see how fast these things are expanding is kind of cool. It's hard though, because trying to eyeball exactly where that region, that circular region should touch that point in the two photographs. If it's off just by a tiny bit, you get a pretty different answer as far as the velocity that piece is moving at. But with a lot of class data, the answers are pretty good.
That sounds like a great activity also to showcase why we like to take a lot of data. One data point is not usually sufficient.
Yeah, there is in that handout, I think I have a sample spreadsheet to give some ideas too of how you could use a spreadsheet, a class spreadsheet to put things into. There's definitely a lot of calculations with that, and it's a complicated activity.
I have one more question. Can anyone suggest some resources that go in a more systematic way I need to read to understand? Like a textbook, online course, summer courses, anything that is helpful for a high school teacher?
Resources as far as resources for a whole astronomy class?
At the high school level, though. Well, yeah, I will read it, not the kids. So if it's a little bit more advanced, I guess I can go through it.
So I actually do these activities with my students at the end of the year in high school. The first few that we did together are ones that seem to be pretty accessible to high school students. One, I don't know if anybody's, I'm gonna just pull up my old Google Classroom. These lecture tutorials. I'm just trying to remember the name of the book. I'm gonna see if I can find it for you. The lecture tutorials I really like in astronomy, they go in a pretty systematic order. And the videos that go, that the guy that wrote the book put together for his classes, the lecture tutorials, he shows a video and then he has a lecture tutorial, and they're not just like multiple choice questions or spit back the information, but they try to get at student misconceptions. Here. Lecture tutorials for introductory astronomy. So they look like a series of worksheets, but then if you just Google this guy's YouTube channel, he has the actual lecture that goes along with these worksheets, and the worksheets really help students think through what he's saying. There'll be things in the worksheets like student number 1 says this, student number 2 says this. Are they both right? Is one of them right? Is one of them partially right? And why? So it's trying to get at a lot of misconceptions. So I really do like that book. It's good.
Thank you. Yeah, I use typers, and that is something similar for physics when they have the ranking tasks. I'm not sure if you are familiar.
Yep.
They also get them to think which one is correct and rank them. Yeah.
Yeah, so I use those a lot. They're really, really good. And it's so nice that his lectures are online too. So, and that they're tailored specifically for those lecture tutorials.
Well, thank you so much, Pamela. I think this is a good time to stop the recording. But we still have a few minutes left in our time here. So if people want to stick around and ask questions or just chat, that would be great too.
Okay.
So thank you again, Pamela.
You're welcome.